Hi everyone. Today let's talk about chapter 11, Boolean algebras and combinatorial circuits. Sessions 11.1, combinatorial circuits. In a digital computer, there are only two possibilities, written 0 or 1. All programs and data are ultimately reducible to combinations of bits. A variety of devices have been used throughout the years in digital computers to store bits. Electronic circuits allow this storage device to communicate with each other. A bit in one part of the circuit is transmitted to another part of the circuit as a voltage. Thus, two voltage levels are needed. For example, a high voltage can communicate 1 and a low voltage can communicate 0. In this session, we discuss combinatorial circuits. The output of a combinatorial circuit is uniquely defined for every combination of inputs. A combinatorial circuit has no memory. The previous inputs and the states of the system do not affect the output of a combinatorial circuit. And so in chapter 12, we will talk about sequential circuits. And then you can see the comparison between combinatorial circuits and the sequential circuits. So sequential circuits has memories. The previous inputs and the states of the system actually change the outputs. Okay, but in our sessions, we're talking about combinatorial circuits. Once the inputs are fixed, then the outputs are uniquely determined for every combinations of input. So combinatorial circuits can be constructed using solid-state devices called gates, which are capable of switching voltage level speeds. We'll begin by discussing AND, OR, and NOT gates. So here are the definitions. An AND gate receives input x1 and x2, where x1 and x2 are bits, so they're either 0 or 1, and produces outputs denotes x1 and x2. So do you remember the true or false logic table? So this AND is really like the AND in our logic table. If x1 and x2 are true, and then x1 and x2 are true. But if one of them are false, then x1 and x2 is false. So this is very similar. If x1 and x2 are both 1, then x1 and x2 is 1. 0 otherwise. And this is the drawing of AND gates. So far so good. So you have this is the AND gates. You have two inputs and you have one output. Okay, you can think about this as like a semicircle longer, and then you have a vertical line segment there. Okay, that is the AND gate. An OR gate receives inputs x1 and x2, where x1 and x2 are bits, and produce outputs denoted by v1, x1 or x2, where x1 or x2 is 1 if one of them is 1 and is 0 otherwise. So it's really matched our logic operator OR for the true or false logic table. Okay, it is true if one of them is true. It is false if both of them are false. So the OR gates the shape like this. So it really like doesn't look like a fish. Okay, so that is the OR gate. And then a NOT gate or inverter receives input x, where x is a bit, and produce output x bar. That's like the NOT. So if the input is 0, then the output is 1. If the input is 1, the output is 0. So really like the NOTs in our logic operator. Okay, so the NOT gate is a triangle, and then you have a little circle attached to it. Okay, so that is the NOT gate. You can see the AND gate, OR gate, we have 2 inputs and 1 output. The NOT gate, we have 1 input and 1 output. Alright, let's continue. So how to evaluate circuits? So we use logic tables. So the following are the logic tables for the basic AND or NOT circuits. So the AND gates, you can see it is 1 if both of them are 1 and it's 0 otherwise. Okay, the OR gates, if one of them have 1, then the result is 1. If both of them are 0, the result is 0. The NOT is just 1 becomes 0, 0 becomes 1. We note that performing the operator AND OR, it is the same as taking the minimum or maximums of the 2 bits x1 and x2. You can see the AND is like the minimum, right? Here, minimum of 1 and 0 is 0, minimum of 0, 1 is 0. And then the OR is like the maximum of 1 and 0 is 1, maximum of 0, 1 is 1. So far, so good, everybody. Let's continue. So, how to evaluate a particular circuit for particular values? Okay, so here we have a combinatorial circuit. And do you remember the symbol? This is AND, this is OR, this is NOT. Okay. Alright, if we want to draw a Boolean expression, so we'll talk about more what is Boolean expression in the next section. Okay, so Boolean expression, in this case, you can see this guy, we have x1 and x2, and then we have OR x3. So we have x1 and x2, and the next step we have OR x3, and the last step we have NOT. So this is the Boolean expression. So far, so good. Okay, so let's evaluate. Okay, so first of all, I want you to see, look at this. Well, this guy is OR. So if x3 is 1, whatever or 1, okay, whatever or 1 is gonna be 1. Not 1 is 0. So here x3, when it's 1, then I don't care what x1, x2 is. The x1 and x2 or x3 is gonna be 1. Not 1 is 0. So we can fill these with zeros. So far, so good. Okay, and then here, let's continue. So for the rest, okay, 1 and 1 is 1, and then 1 or whatever is 1, and then not 1 is 0, so we get 0. Okay, with this guy, 1 and 0 is 0. 0 or 0 is 0, not 0 is 1. Are you okay, everybody? So don't forget you can pause the video at any time, and if you want, you can write more detail to take notes. Okay, this guy, 0 and 1 is 0, 0 or 0 is 0, not 0 is 1. This guy, 0 and 0 is 0, 0 or 0 is 0, 0, not 0 is 1. So far, so good, everybody. So this is how we figure out the logic table. Let's continue. Okay, this example, we have x1, x2, x3. This is NOT gates. This is, this is AND gates. This is OR gates. Okay, if we want to write down the Boolean expression, we're gonna have first NOT x3, right? And then we use it to AND x2, and then we use it to OR x1. So far, so good, everybody. Okay, how to figure out the logic table? Well, because let's look from the outside to the inside. OR, so if x1 is 1, 1 or whatever is 1. So if x1 is 1, 1 or whatever is gonna be 1. Okay, that's easy. See, we already figured out 4 of them. Okay, the rest, let's look at each of them. Here, x3 not 1 is 0. 0 and 1, 0. 0 or 0, 0. So this is 0. And then this guy, not x3. So not 0 is 1. 1 and 1 is 1. 1 or 0 is 1. Here, not 1 is 0. 0 and 0, 0. 0 or 0 is 0. Here, not x3, so not 0 is 1. But 1 and 0 is 0. 0 or 0 is 0. Nah, and then so the answer is 0. So far, so good, everybody. All right. Do you have the same answer? Yeah, so before we continue the problem, you can pause the video and try to work on the problem first. And then after you're done, you can go ahead and play the video and check your answers. Okay, now we have ABC. Oh, so let me change this guy to ABC. Well, this is, what is that? This is, and this is not. This is, or this is not. Okay, so we have A and B, and then we want it or not C, and then not everybody. Okay. Do you remember the De Morgan's laws? So actually we can use De Morgan's laws to simplify this guy. So remember, the not is like the negative number. When we distribute it, we have A and B. It flipped the N and OR. So this guy, it was OR. Now it becomes N. And then C, not C is just C, right? And then you want to move this not inside. We have this guy, and then it was N, now become OR, complement, and then okay. All right. So of course, you don't have to do this. You can evaluate this guy, or you can evaluate that guy. It's up to you. Okay. I just think when I distribute the not, maybe sometimes it's easier, but it's a good exercise. Maybe you can do both. Okay. So this is an exercise at home. So after you watch the videos, please do this guy. Okay. Do the logic table for this guy. Okay. So let's look at this. It's N. So which means if C is 0, okay, whatever and 0 will give us 0. So C is 0 here, 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 here. So that will give us 0, 0, 0, 0. See, isn't it nice? We already figured out a lot of it. Okay, so let's continue. And then let's look at the first one. So not 1 is 0. 0 or 0 is 0. 0 and 1 is 0. Okay, next. 0 or 1 is 1. 1 and 1 is 1. Here, 1 or 0 is 1. 1 and 1 is 1. Here, 1 or 1 is 1. 1 and 1 is 1. So far, so good, everybody? Okay, good. Let's continue. So here we have more examples. But let's not do the whole logic table. Let's just look at some specific values. Let's say if this is 1, this is 0, how does this change? Okay, 1, this is a not gay. So after the not gay, it becomes 0, right? And this is not gay, so it becomes 1. And then this guy is an AND gates, right? The AND gates 0 and 1 is 0. And then this guy, what this guy means is 1 and 0 give us 0. 0 or 0 give us 0. So far, so good, everybody? So you can see, besides looking at the Boolean equations, expressions, and figure out the logic table, we can also like start with some values and then look at this picture. So what happened? How does those values change after we go through each gate? Okay, so far so good, everybody. Let's continue. Oh, so here we have x1, x2, x3, right? Let's pick some number. Let's say it's 110. So let's see what is the output. So this is a not, okay? It becomes 0, and then here, because it's 1, this is OR. So 0 or 1 is 1. This is and let's say here, this is okay, so this is 0, but not 0 is 1. This guy is, the input is 1, and 1 will give us 1. How about this guy? This guy is let's see, this guy is AND. So we have 1 and 0 give us 0. Okay, this guy is also x1, so it's 1 or 0 give us sorry, this is AND. 1 and 0 give us 0. Okay, and then this guy is 1 or 1 is 1. This is 1 and 1 is 1. Finally, this is OR. 1 or 0 give us 1. So the answer is 1. So far, so good, everybody? Yeah, so we can also look at the circuits, and then we can imagine how those the beat flows, okay, through the gates. Let's continue. A switching circuit is an electric network consisting of switches, each of which is open or closed. An example is given in the figure. If switch X is open, then we write X is 1. I think it's 1, okay. If it's open, then we say X is 1. And if, oh, sorry, yes, it's open. Okay, if it's open, then the circuits cannot go through, then we say X is 0. If it's closed, then it can go through, so we can have X is 1. The switches labeled with the same letters, such as B in the figure, are either all open or all closed. Switch X, such as A in the figure, is open even only if the switch X bar, such as A bar, the not A, is closed. So if A is open, then A bar is closed. If A is closed, then A bar is open. Okay, because they're not. Okay, if current can flow between the extreme left and right ends of the circuits, we say that the output of the circuit is 1. Otherwise, if the current, the output of the circuit is 0, then the current cannot flow from the left to the right. So a switching table gives the outputs of the circuits for all values of the switches. Okay, so let's look at this. How do we write down a Boolean expression? Well, here, if there are 3 choices, you can use OR to connect them. And within here, you use AND to connect them. So for this circuit, we have A and B. And then this guy, we have A complement. This guy, we have B and C. So between those 3, we use OR. So far, so good, everybody? Okay, next. Let's look at this table. Let's check it. Okay, so ABC, 1, 1, 1. So if it's 1, which means it's closed, then the current can flow this way, right? That's why it's 1. I don't care what the C is. We can flow through this way. So if A, B are 1, then our result is 1. So this guy is also 1. Let's go to the next. A is 1, B is open, B is open. So B is open, so you cannot go these two ways. And because A is closed, then A bar is open. Then this is, you cannot go to any of those three ways. So that's why we get 0. And then next we have A is closed, B and B. Okay, you can see when B is open and A complement, so A bar is also open, so we cannot go through this way too. Okay, so next, well, can you see all of these? Because A is open, then the A bar is closed. A bar is closed. Good. We can always go through the middle way. So that's why we all get 1s. So far, so good, everybody? Okay, let's continue. So represent each circuit symbolically and give a switching table. So here we have A. So it has to go through A, and then that's why we use the and then we have two ways. So we have a parentheses is either B, or we can have C followed by B bar. So far so good, everybody? Okay, now let's see. So first of all, you can see if A is open, then the circuits, the currents cannot go through, right? So all of these we have 0s. Okay, if A is 1, then let's look at B. If B is 1, yeah, we can go through this way. So we can go through this way. So we can go through, then we put 1 there. Okay, if A is 1 but B is 0s, then B complement will be closed. Okay, then look at C. If C is closed, then we can go through this way, right? But when C is open, then we cannot go through. So that's why this is the switching tables. So far, so good. So we look at the circuits, and then we can imagine what happened to the currents whether they can go through for each switch. Okay, let's continue. Next, represent the expressions. So here we have the symbolic expression. We want to express as a switching circuits, and we want to write down the switching tables. All right, let's see. So if it's and, then we means we have this guy. So this is what I mean by saying and. Okay. So when do you use or? So or means you separate into two ways. So this is or. Okay, so this is or, so which means we separate into two ways. One way is A complement, A bar, and B, so A, B. So B here, A bar right here. The other way, C and A. So we have C and A. So that is the circuits, the switching circuits. So far, so good, everybody? Okay, let's see. Okay, so let's look at this one. Let's look at the first path, okay? We can pass through if A complement is closed, which means when A is open is 0. And when B is closed, so this guy. So this is the first path. We can put 1 right here. The second path, CA. So CA means we must have the C is 1 and the A is 1. So A has to be 1 and C has to be 1 as well. So this is 1. So because those are the only two paths, which means all of the others are 0s. Is that okay? So this is one way you can look at each path. Okay, you look at the first path. When you can go through, right? So the first path here we have A bar and B. So that's when A is 0 and B is 1. We can go through. Okay, so we find those two. And then next, the second path, we have C and A. So we find when C is closed, so C is 1 and A is 1. So we can go through and get 1. So those are the only two paths we can go through. So all the rest is going to be zeros. So far, so good, everybody. So that is the switching circuits. Now you're ready to complete your homework about sessions 11.1. And when you have questions, feel free to ask me in class or office hours or email me. Have a nice day. Bye.